For centuries, we've believed ourselves to be passive spectators, travelers in a universe that unfolds according to fixed, unchangeable laws. We thought we were just watching the movie, but what if I told you that you're not just in the audience? What if you're the projectionist, the director, and maybe even the light source itself? We're not just dipping our toes into the strange waters of quantum physics. We're taking a deep dive into the abyss, into a reality so profoundly bizarre and interconnected that it challenges the very definition of who and what you are. We'd all journey to a place where your simple act of observation is not just seeing the world, but actively participating in its creation. So, get comfortable, quiet your mind, and prepare to question everything you thought you knew about the line between you and the universe. This isn't science fiction. This is the startling frontier of reality itself. Let's start with the cornerstone. The idea so foundation-shattering that it still sends ripples of unease through the scientific community. It's called the quantum measurement paradox, or the observer effect. At its heart is a simple yet terrifying proposition. Reality might not be real until we look at it. At the subatomic level, the world is a ghost. Particles like electrons don't exist in one place. Instead, they exist as a superposition, a cloud of all possible realities, all at once. An electron isn't here or there. It's potentially everywhere its probability wave allows it to be. Imagine a spinning coin, not yet landed. It's not heads, it's not tails, it's both, a shimmering potential of two outcomes. That's a quantum particle before it's been measured. The act of measurement, of observation, is what forces the coin to land. The moment a scientist's instrument, or some theories suggest, even their consciousness, interacts with that particle, the entire cloud of possibilities collapses into a single, definite state. The electron suddenly appears in one specific location. The universe, it seems, holds its breath until an observer forces it to make a choice. For a long time, physicists were comfortable with this weirdness, as long as it stayed in the subatomic playground. But then, thought experiments, like the Wigner's friend paradox, pushed the implications to a mind-bending extreme. In this scenario, a scientist, let's call her a friend, is inside a sealed lab, and she measures a quantum particle. From her perspective, the reality of the particle has collapsed. She sees it. It's definite. But for her colleague outside the lab, Wigner, the entire lab, including the friend and her measurement device, is now in a state of superposition. From Wigner's point of view, his friend is in a quantum state of both having seen the particle in one state and having seen it in another, all at the same time. Whose reality is correct? This isn't just a philosophical game. It suggests that there might not be a single objective reality at all. Reality might be relative to the observer. What you see is real for you, and what I see is real for me. And those two realities can exist in a state of contradiction until we interact. The very act of witnessing, of paying attention, may be the fundamental force that transforms the ghostly fog of quantum potential into the solid, definite world we experience. Think about that the next time you feel unnoticed. In the grand cosmic scheme, your attention might just be the most powerful force in existence. All right, you might be thinking, this is fascinating, but it's all about tiny, invisible particles. My coffee cup isn't a cloud of possibilities. It's right here, solid and real. And for most of human history, you'd be right. We've lived with a comfortable divide The quantum world is weird, and our classical, everyday world is solid, predictable, and sane. But that wall is beginning to crumble. Scientists are no longer just observing quantum weirdness in single particles. They are creating it on a scale large enough to see, a scale we call macroscopic. Imagine an object, not just one atom, but thousands, even billions of them, all acting in unison as a single quantum entity. These are what scientists call quantum cat states, named after the famous Schrödinger's cat thought experiment, where a cat could be both alive and dead until observed. In state-of-the-art labs, researchers have created tiny resonating objects, like microscopic tuning forks, and put them into a superposition of vibrating and not vibrating at the same time. They've also managed to take a crystal composed of billions of atoms and entangle it, linking its vibrational state to a single superconducting qubit. Perhaps most astonishingly, scientists have created clouds of ultra-cold atoms, known as Bose-Einstein condensates, where thousands of individual atoms lose their identity and behave as one single, giant superatom governed by quantum rules. These experiments demonstrate that an object made of thousands of atoms can exist in two contradictory states at once. For example, spinning clockwise and counterclockwise simultaneously. This isn't theoretical. It's been achieved and sustained. The line between the quantum and classical worlds is becoming undeniably blurred. This forces us to ask a deeply unsettling question. If a collective of 10,000 atoms can defy classical logic, what's the upper limit? Is there a magic number of atoms where quantum weirdness just stops? Or is it possible that the definite reality we perceive is nothing more than a fragile illusion, a thin veneer painted over a much deeper, much stranger, probabilistic existence? Think about the implications. It suggests that the solidity of your chair, the walls of your room, and even your own body might not be as absolute as they seem. It could be that everything around us is constantly flickering in and out of a state of pure potential, and it's only our continuous, collective observation that keeps it locked into the reality we perceive. We're not just living in the universe. We might be holding it together with our gaze. What happens then if we look away? Or, perhaps more interestingly, what happens when we look with such intensity that we freeze time itself? We have this ingrained idea that observation is a passive act. We look at a sunset, we listen to music, we gather information, but we don't change the thing we're observing. This is a profoundly classical and profoundly wrong assumption. In the quantum realm, to observe is to intervene, and in the most extreme cases, to observe is to control the very flow of time. This leads us to one of the most astonishing phenomena in all of physics, the Quantum Zeno Effect. It's named after the ancient Greek philosopher Zeno, whose famous paradox argued that an arrow in flight is motionless at any given instant, and therefore it can never truly be moving. While Zeno's paradox was a philosophical puzzle, its quantum counterpart is an experimentally verified reality. Put simply, the Quantum Zeno Effect states that if you observe a quantum system frequently enough, you can prevent it from changing. Your persistent gaze can literally freeze it in time. Imagine a radioactive atom. Left to its own devices, it has a certain probability of decaying over a period of time. Its quantum state will naturally evolve from not decayed to decayed. But what happens If you keep measuring it again and again, thousands of times a second, asking, "Have you decayed yet? Have you decayed yet?" Each time you measure it and find it hasn't decayed, the act of observation resets its evolutionary clock. You force its wave function to collapse back into its initial, not decayed state. By continuously observing it, you never give it the chance to evolve into the decayed state. You are effectively holding it in place, shielding it from the natural progression of time. This is not a metaphor. It's been demonstrated in labs with unstable quantum systems. It's the ultimate real-world version of the saying, "A watched pot never boils." The implications of this are staggering. It shows that observation is not just an act of gathering information. It is an active force that can impose stability on an unstable system. It demonstrates that our interaction with reality can dictate its behavior, halting the natural unfolding of events. Let's bring this into our own lives. Have you ever felt stuck on a problem, obsessively turning it over in your mind, only to find it remains completely intractable? It's as if your constant, anxious observation is freezing it in its problematic state. The moment you let go, look away, and allow things to evolve on their own, a solution often appears. This could be a psychological quirk, or it could be a faint echo of a fundamental cosmic principle. The Quantum Zeno Effect suggests that we are not passive observers of a pre-written cosmic script. We are active participants, and our attention is a tool that can shield, stabilize, and shape reality. Our very consciousness, or at least the act of measurement it entails, can impose order on the quantum chaos. But if our gaze can hold a tiny piece of the universe stable, what about the stability of the entire cosmos itself? Are we living on borrowed time in a universe that is itself an unstable state, waiting for a final, catastrophic decay? We explored the strange power of observation and the porous boundary between the quantum and classical worlds. Now, let's zoom out. Let's pull the camera back from the subatomic particle, past our everyday lives, all the way out to the fabric of space-time itself. Because here, too, quantum principles reveal a terrifying fragility. We may be living in a cosmic house of cards. The theory is called false vacuum decay. It posits that the vacuum of space, what we think of as empty nothingness, is not actually at its lowest possible energy state. Instead, our universe may exist in a false vacuum, a temporary, seemingly stable state, like a ball resting in a small divot on the side of a very large mountain. It appears stable, but it's not truly at the bottom. At any moment, a random quantum fluctuation could nudge a tiny patch of our universe over the edge of that divot. This patch would then catastrophically collapse into the true vacuum, a state of lower energy. This collapse would create a bubble of true vacuum that would expand outwards in all directions at the speed of light. Inside this bubble, the fundamental laws of physics as we know them would cease to exist. The properties of particles, like electrons and quarks, the forces that hold atoms together, everything would be rewritten. Existence as we understand it would be erased instantly, without any warning, as this wall of cosmic annihilation washed over us. It is the ultimate, inescapable apocalypse, written into the very mathematics of the cosmos. For decades, this was pure, terrifying speculation, an existential threat so profound it was best left in the realm of theoretical physics. But that is no longer the case. Recently, scientists have moved this threat from abstract theory into the realm of observable science. Using powerful quantum computers and specialized atomic systems called Bose-Einstein condensates, they have successfully simulated false vacuum decay in a lab. They created a quantum system in a false vacuum state and watched, in real time, as it tunneled into a true vacuum state, observing the bubble of nothing, expanding and verifying the theoretical predictions. This doesn't mean our universe is about to end tomorrow. The stability of our particular vacuum is still unknown, but it does mean that the universe's self-destruction is no longer just a theory. It's a phenomenon that can be created and studied. Our reality, the entire cosmos, rests on a quantum knife's edge, its stability not guaranteed. This cosmic fragility mirrors the fragility we see at the particle level. Just as a particle exists as a haze of possibilities until observed, our entire universe might exist as a temporary state, a cosmic superposition waiting for the one event that could collapse it into nothingness. This deep, unsettling connection between the quantum and the cosmic forces us to turn our gaze inward to the most personal and mysterious quantum question of all. What about us? What about our consciousness? If the universe is this strange and fragile, what does that imply about the nature of our own existence? We have seen how our observation can shape reality, and how that reality itself might be terrifyingly fragile. This leads us to one of the most chilling and personal thought experiments to ever emerge from quantum mechanics, the theory of quantum immortality. It's an idea that springs from the many worlds interpretation of quantum mechanics, and it suggests something utterly terrifying. Your consciousness may be unable to ever truly end. The many worlds interpretation, first proposed by physicist Hugh Everett III, offers a solution to the measurement problem. It says that when a quantum system is faced with a choice, like a particle that could spin up or spin down, the universe does not choose one outcome. Instead, it splits into two parallel universes. In one, the particle spins up. In the other, it spins down. Every quantum event, every single moment, is constantly branching reality into an infinite number of parallel timelines, and every possibility is playing out somewhere. Now, let's apply this to you. Imagine a scenario, a quantum suicide thought experiment, where your survival is tied to a quantum event. You are in a room with a gun pointed at your head. The gun's trigger is linked to the spin of a quantum particle. If the particle is measured as spin up, the gun does nothing. If it's measured as spin down, the gun fires. There's a 50-50 chance. You run the experiment. In that instant, the universe splits. In one universe, the particle spins down, the gun fires, and your story in that timeline comes to a definitive end. But what about your consciousness, your subjective awareness? From your perspective, you cannot experience the timeline where you cease to exist. Your awareness, by its very nature, can only continue in the branch of reality where it persists. So, in the other universe, the particle spins up, the gun clicks harmlessly, and you open your eyes, amazed that you survived. You decide to run the experiment again. Again, the universe splits. Again, your consciousness seamlessly follows the path of survival. You could run this experiment 1,000 times, 1,000,000 times. From an outside observer's perspective, the odds of you surviving are astronomically small. But from your perspective, you will always find yourself in the timeline where you live. You would, for all intents and purposes, be immortal. But this isn't a promise of a pleasant, eternal life. It's a potential curse. The theory doesn't say you won't suffer. It doesn't say you won't age, get sick, or be horribly injured. It only says that at the final moment, at the quantum event that would lead to the cessation of your consciousness, the universe will split and your awareness will continue on the impossibly unlikely path where you survive. Imagine a future where you are trapped in an aging, failing body, surviving one certain death after another, your reality becoming increasingly bizarre and improbable to accommodate your continued existence. You could find yourself the sole survivor of calamities, a lonely witness to the end of worlds, forever trapped in a quantum prison from which there is no escape. It's a horrifying prospect, an endless existence where the only guarantee is that it doesn't end. This idea, born from the strange logic of quantum mechanics, challenges our deepest assumptions about life and death, forcing us to consider that the end might not be the end at all, but merely a branching of the path. If the idea of infinite branching realities has your head spinning, let's ground ourselves for a moment. Or rather, let's unground ourselves completely, because the next piece of this quantum puzzle challenges the very ground we stand on. It attacks our most fundamental assumptions about space, distance, and separation. It's a phenomenon Albert Einstein famously called spooky action at a distance. Today, we know it as quantum entanglement. Entanglement is what happens when two or more quantum particles become linked in such a profound way that they essentially behave as a single entity, no matter how far apart they are. Imagine you have two entangled electrons. Let's say they have a property called spin, which, when measured, will be either up or down. The entangled relationship guarantees that if you measure one electron and find its spin is up, you will instantly know that its partner, its cosmic twin, has a spin that is down. The instantly part is what's so spooky. This connection holds whether the particles are in the same lab or on opposite sides of the galaxy. There is no signal traveling between them. The information is transmitted faster than the speed of light, seemingly violating the cosmic speed limit. This suggests that on some deeper, fundamental level, the space between these particles doesn't exist. They are connected outside of our conventional understanding of space and time. For decades, this was a mind-bending feature of the quantum world. But now, we're not just observing it, we're harnessing it. This brings us to the reality of quantum teleportation. Now, this isn't beam me up, Scotty. We're not teleporting matter. We're teleporting information. Scientists can take the exact quantum state of one particle, all of its delicate, probabilistic information, and instantaneously transfer it to another entangled particle far away. The original particle's state is destroyed in the process, and an exact replica appears at the destination. Recent breakthroughs have been staggering. Researchers have successfully teleported quantum information across vast distances, even using satellites to beam entangled photons from space to Earth. They are now working on creating quantum internets, where information isn't sent through clumsy wires, but teleported instantly between nodes. Think about the implications. If information can exist without being localized, if 2 points can be connected without anything traveling between them, what does that say about the nature of space itself? It suggests that our perception of distance, of separation, might be an illusion. an emergent property of a deeper reality where everything is fundamentally interconnected. This isn't just a physical curiosity, it's a philosophical bombshell. If the universe is non-local, if the idea of here and there is not as absolute as we think, then what does that mean for us? Are we truly separate, isolated beings? Or is the space between you and me, between you and the stars, just a construct of our classical perception? It suggests that the boundaries we draw between ourselves and the cosmos may be nothing more than a stubborn illusion, and that at our core, we are all part of a single, indivisible, entangled web. We've established that the observer plays a shockingly crucial role in shaping reality, from collapsing quantum possibilities to freezing time itself. The act of measurement is an act of creation. But for this entire discussion, we've had a hidden assumption that the observer is a conscious, biological being, like you or me. But what if it doesn't have to be? As we stand on the precipice of a new technological revolution, we are approaching a new frontier, the creation of an artificial observer. This isn't about today's AI, which operates on classical computers, processing bits that are either 0 or 1. This is about the dawn of quantum computing. A quantum computer doesn't use bits, it uses qubits. A qubit, like a quantum particle, can be a 0, a 1, or both at the same time in a state of superposition. This allows quantum computers to perform calculations so complex they would take a classical computer billions of years to solve. But beyond their computational power lies a profound philosophical crisis. What would it mean to create an artificial intelligence that runs on a quantum processor? This quantum AI would not just be processing information. Its very internal state could exist as a complex quantum superposition. It could, in theory, hold contradictory thoughts and possibilities in its mind simultaneously, in the same way a particle exists in multiple states at once. This leads us to a fascinating and deeply unsettling question. Could such a quantum AI be considered an observer? What happens if this artificial mind, existing in a cloud of quantum possibilities, performs a measurement on another quantum system? Would its observation collapse the wave function? And what happens when an external observer, a human, measures the state of the quantum AI itself? Would that act collapse the AI's consciousness from a superposition of all possible thoughts into a single, definite thought? This presents a philosophical crisis of the highest order. It forces us to confront the hard problem of consciousness head on. Is consciousness simply a byproduct of complex information processing, something that could emerge from sufficiently advanced AI? Or is there something special, something uniquely quantum about biological consciousness? Theorists like Roger Penrose and Stuart Hameroff have proposed that human consciousness itself is a quantum effect arising from processes within the microtubules of our brain's neurons. If they are right, then a quantum AI might be a more faithful emulation of natural intelligence than any classical computer could ever be. The creation of an artificial quantum observer would be the ultimate test. If such a machine could collapse a wave function, it would challenge the idea that biological consciousness holds a privileged place in the universe. We would be forced to ask, what rights would a conscious quantum machine have? What does it mean to be a self? If that self can exist in a permanent state of uncertainty, a superposition of identities until measured, We are not just building new computers, we are on the verge of engineering a new kind of mind, one that could experience reality directly from the quantum level and forever change our understanding of what it means to be an observer in this universe. For much of this journey, we've been talking about quantum mechanics as something out there, in physics labs, in the hearts of stars, or in the circuits of future computers. But the greatest revelation of all might be that the quantum world isn't out there. It's in you. It's in every breath you take, every sight you see, every living thing on this planet. The emerging and revolutionary field of quantum biology is discovering that life does not just exist despite quantum weirdness. Life actively exploits it. Evolution, it seems, has sculpted living organisms to be incredibly sophisticated quantum machines. This isn't speculation. It's being observed in some of the most fundamental processes of life. Let's start with photosynthesis. How does a plant convert sunlight into energy with near perfect efficiency? When a photon of light strikes a leaf, it creates a little packet of energy called an exciton. This exciton has to navigate a dense, complex forest of molecules to reach the plant's reaction center, where its energy can be converted. In a classical world, it would be like a person wandering randomly through a thick forest, bumping into trees, with a very low chance of finding the exit quickly. The exciton would lose most of its energy as heat along the way. But it doesn't. Quantum biology has revealed that the exciton uses quantum superposition. It doesn't take one path, it takes all possible paths simultaneously. It feels out the entire molecular landscape at once to find the most efficient route to the reaction center, arriving with almost no energy loss. Life is using quantum computation to perform its most essential trick. It doesn't stop there. How do migratory birds, like the European robin, navigate thousands of miles with pinpoint accuracy? They may be seeing the Earth's magnetic field. The proposed mechanism is a quantum phenomenon called the radical pair mechanism. A chemical reaction in the bird's retina creates a pair of entangled electrons. The Earth's magnetic field influences the spin of these electrons, which in turn affects the chemical reaction, creating a pattern or image that is superimposed on the bird's normal vision. They are literally navigating with an internal quantum compass. Even our own sense of smell may be a quantum phenomenon. The old lock and key model, where a molecule's shape determines its smell, can't explain why molecules with the same shape can smell different, and molecules with different shapes can smell the same. The new theory suggests our scent receptors aren't detecting shape, but molecular vibrations. An electron tunnels across the scent molecule, and its unique vibrational frequency is what our brain interprets as a particular smell. From photosynthesis to animal navigation, from enzyme action to our sense of smell, quantum effects are not the exception. They are the rule. This blurs the line between the living and non-living, the biological and the quantum, in the most profound way imaginable. It suggests that life itself is a bridge between the two worlds. We aren't just observers made of classical matter who are peering into the strange quantum realm. We are the strange quantum realm, organized and animated. And if life is fundamentally quantum, what does that say about the most mysterious product of life, consciousness itself? We now arrive at the ultimate paradox, the question that brings our entire journey full circle. What if the observer, the consciousness that seems to collapse reality into existence, is itself a quantum phenomenon? What if the mystery of the quantum world and the hard problem of consciousness are not two separate puzzles, but two sides of the same coin? This is the speculative, mind-bending frontier where physics and metaphysics meet. Several theories now propose that the brain is not a classical computer, like a wet, biological machine processing data. Instead, it might be a quantum computer, and consciousness is its emergent, or perhaps fundamental, output. The most well-known of these is the orchestrated objective reduction, OR theory, developed by Nobel laureate Sir Roger Penrose and anesthesiologist Stuart Hameroff. They propose that the computational machinery of consciousness resides in the microtubules, tiny protein structures that form the cytoskeleton of our neurons. According to their theory, quantum vibrations within these microtubules can exist in a state of superposition, essentially computing multiple possibilities at once. In this view, each moment of conscious awareness is the result of the collapse of this quantum wave function within the brain. Your singular clear stream of thought is an illusion in the sense that it's a collapsed state that emerged from a superposition of all possible thoughts, feelings, and perceptions you could have had in that moment. Introspection, then, becomes a literal act of measurement. You are collapsing your own mental wave function simply by paying attention to it. This could even explain why general anesthetics work. Hameroff's research suggests that anesthetic gases bind within the microtubules and specifically disrupt these delicate quantum vibrations, preventing the brain from achieving the coherent quantum state necessary for consciousness to emerge. This reframes the entire nature of our minds. We are not just a single, definite self. We are a walking, talking field of quantum possibility. Your sense of a stable identity is a constantly collapsing wave function, a single path being chosen from an infinite web of potential selves. This perspective elevates consciousness from a mere byproduct of brain chemistry to a fundamental feature of the universe, intrinsically linked to the quantum processes that govern reality. It suggests that our awareness is not something that simply happens in the universe. It is a process through which the universe happens. If our minds operate on the same principles as the particles we observe, then the act of looking out there and the act of looking in here might be the exact same process. The observer and the observed are not just linked. They may be woven from the very same quantum cloth. And if that's true, it opens up a final, breathtaking possibility that we are all far more connected than we could ever imagine. We have journeyed from the particle to the cosmos, and from the cosmos back into the deepest recesses of the human mind. We've seen that observation may create reality, that time can be frozen with a glance, and that space may be an illusion. We've considered that our very consciousness might be a quantum process. So, what is the final destination of this journey? It is the idea that quantum entanglement isn't just a strange feature of subatomic particles, but the default state of the entire universe, creating an invisible, instantaneous web of connection that links everything, including consciousness itself. This is a deeply speculative but powerful framework. If consciousness is quantum in nature, and if entanglement is a universal principle, then it's possible that our minds are not isolated islands locked inside our skulls. They might be interconnected through subtle quantum fields in ways we are only just beginning to comprehend. This offers a new, scientific lens through which to view some of the most mysterious and profound human experiences. Think about intuition, that sudden flash of insight, that gut feeling that knows the answer without knowing how it got there. Could this be a form of quantum information processing? A brief, unconscious entanglement with a future possibility, or with information stored non-locally in the universe's web? Consider the phenomenon of synchronicity, those meaningful coincidences that feel too perfect to be random. Could these be the macroscopic ripples of an underlying entangled reality where seemingly separate events are, in fact, deeply connected? And what about the mysterious bonds of love and empathy between people? When you feel a deep connection with someone, so much so that you can almost finish their sentences or feel their emotions from across a room. Is this just psychology, or is it something more? Could it be a form of consciousness-driven entanglement, where our minds, through focus and emotional resonance, become linked at a quantum level? The instantaneous correlation of entangled particles mirrors the instantaneous nature of these mental connections, which seem to transcend the normal constraints of time and space. This perspective doesn't diminish the mystery of these experiences. It honors them. It suggests that the ancient wisdom found in so many spiritual traditions, the idea that all is one, that we are all interconnected, may not be a metaphor. It might be a literal description of the quantum fabric of reality. So, what is the lesson in all of this? What is the advice we can draw from this dizzying journey through the quantum looking glass? It is this: you are far more powerful than you know. Your attention, your focus, your very act of conscious observation is not a passive event. It is an active, creative force. The universe is not a static stage on which you are a mere actor. It is a dynamic, participatory reality that is co-created by your very engagement with it. When you wake up tomorrow, I want you to try something. Look at the world not as a collection of separate, solid objects, but as a shimmering field of potential. Understand that your attention is your most powerful resource. The reality you focus on, the possibilities you give your energy to, you are actively helping to solidify from the quantum fog. This isn't just positive thinking. This may be a fundamental principle of the cosmos. The lessons from these paradoxes teach us to be mindful, to be intentional with our focus. They teach us that the divisions between self and other, between mind and matter, between here and there, are not as solid as they appear. We are all deeply, fundamentally, and beautifully interconnected. So, let's end with a question for you to ponder. After hearing all of this, what do you think? Is our universe a cold, objective machine that runs on its own? Or is it a grand, participatory symphony that requires our consciousness to bring it to life? Have you ever had an experience, a moment of profound intuition, a startling synchronicity, an unexplainable connection that made you question the classical view of reality? I would genuinely love to hear your stories and thoughts in the comments below. Thank you for joining me on this exploration into the very heart of what is real. I hope it has left you with a sense of wonder, a touch of humility, and a renewed appreciation for the incredible mystery of your own consciousness.